So hello and good morning to everyone. So our today's lead code question is 2770, which is maximum number of jumps to reach the last index, right? So basically in this question we are given a zero indexed integer array named as nums and whose size is and we are also given an integer target, and initially we are at index number 0, and in one step we can jump from any index from index I to any index j such that j should be greater than the current index I, and the difference of the element present at index j and index I, that is nums of j minus nums of I, should be in the range from minus target to target, right? That difference should lie in the range. Then we can jump from index I to index number j, right? And what we have to do is we have to return the maximum number of jumps. We have to return the maximum number of jumps to reach the index I n minus 1 from index 0, like 0 to n minus 1. And what is the max number of jumps? And if there is no way to reach index n minus 1, then we have to return minus 1, right? So let's see examples to get the question more clearly. So in the first example we are given the nums array is 1 3 6 4 1 2 and the target is 2, means the difference of the two values should be in the range minus 2 to 2, and we are present at index number 0. So first, can we go to index number 3? Yes, we can go because the difference is 2. Then from 3 can we go to 6? No, the difference is 3. From 3 can we go to 4? Yes, the difference is 1, we can go. From 4 to 1? No, 4 to 1 is not possible. Then 4 to 2? Yes, it is possible as the difference is 2. So how many jumps we have taken? 1, 2 and 3. We have taken 3 jumps. So the output here is 3, as the maximum number of jumps that we can take is 3 only, right? Let's see the example number 2. So here we are given with the same array 1 3 6 4 1 2, but our target value is 0 now. That means the difference of the value should be 0. So initially we are at index number 0 that has value 1. That means we can jump to another index which has the same value. So we have jumped to this index having the same value. Now from here we can't jump to any future index because there is no future index having the same value. So there is no way we can reach n minus 1, right? So hence we have written minus 1. So let's move to the constraint part. So nums dot length, which is the n, so n is up to 10 ki power 3, right? And each element in the nums array can be from minus 10 ki power 9 to 10 ki power 9, right? And our target can be any value from a value up to 2 into 10 ki power 9. This is the target value. So here see, n is 10 ki power 3. That means n square will be 10 ki power 6. So we can so like due to these complexities, n square won't give us TLE, like n square will be a feasible solution. It will be a feasible solution to us, right? So we can think of some solution of n square, right? So let's start. So in this video I'll be explaining you the brute force approach, that is n square approach using DP, and I'll also be explaining you the same solution using segment tree, right? So please watch it completely. So here our problem asks the maximum number of jumps to reach n minus 1 from index number 0. So here see, whenever we are asked for maximum or minimum jumps, then the first natural choice which hits our mind is DP, right? So we have declared, so dp of I is basically the maximum jumps needed to reach index number I, right? So that is dp of I. So suppose if dp of I is equal to 5, that means to reach index I from index number 0, we need a maximum of 5 jumps. And if dp of I is equal to minus 1, that means this index cannot be reached. Right? So we start. So initially we are at index number 0. Initially we are at I is equal to 0. So dp of 0 will be 0 because we do not need any jump to reach index number 0. We are present at that case. So dp of 0 is equal to 0 will be our base case, right? So let's see how we'll be doing the transition. So here we can either do forward transition, or we can do backward transition, right? Either forward or backward. So let's see what will be in forward transition. So in forward transition, what we'll do is we assume that we are currently at index number I. And then from this index I, we'll jump to all the indexes j. We'll jump to all the possible indexes j, right? And then update their values, right? Update their dp of j values, right? So from current state I, we are taking we are moving to all the future steps j. We are moving to all the future states j, right? So that's why it is forward transition, right? So we are currently at index I, and then we try all future indexes j lesser than greater than I, sorry. And we check if our jump condition is valid. That means the difference of the elements should be in the range minus target to target. If that happens, then we update the dp value, right, by the already stored value or the current value at I plus one more jump we are taking to reach j. So dp of I plus 1. So and we take the maximum of these. So this is forward transition. Similarly, we could have taken backward transition also. So in backward transition, what we assume that we are now at index j. We are now at index j. So what we think is, what are the previous indexes I which are lesser than j? What are the previous indexes I which are lesser than j? From those indexes we can come to j, right? We scan all the previous indexes I. Such that from those indexes we can come to j, right? So we take all the previous indexes I, and then from there we jump to j. So what we do is we'll scan all the previous indexes I, and then take the maximum value. Take the maximum value of the all the previous indexes, right? And then add 1, because from I to j we need one jump, so add 1 to it. So dp of j is equal to 1 plus maximum of dp of I. So if we show it mathematically, so basically it is maximum among all the indexes I lesser than j, and there is a valid jump. So we take dp of I plus 1. So whichever index I gives us this value as the maximum, then we take that value and store in dp of j. So here we have seen both forward transition and backward transition. So I'll be using forward transition and show you, and like you can try out any, like take forward or either backward transition. I'll be using forward, right? So let's see an example, right? So we are given the nums array is 1 3 6 4 1 2, and our target is 2, right? So initially our dp of 0 will be 0, and all the other states having -1. That means they haven't either reached or they can't be reached, right? Then from index number 0, at index number 0 we have value 1, right? We have value 1. So we check all the future indexes where we can jump with this value, right? So see, from value 1, what will be the range will be, it should be between -2 to 2. Difference should be -2 to 2, right? So it can be from 3, and then -2 means, I think, -1 to -3. We can take all the values from -1 to -3, right? So we can jump to 3, we can jump to 1, we can jump to 2. So these are the indexes where we can jump, right? And see here at index number 0 the number of jumps are 0. So we mark the future indexes where we can jump, we mark their dp value as 1, right? So let's see. So first we see j is equal to 1. So at j is equal to 1, the difference is valid difference. So we mark dp of 1. Dp of 1 is equal to maximum of the value stored value is -1, and the current value, that is at 0 plus 1, it's 1. So this way, from I is equal to 0, we check for all j values for all j values, and then update our dp value. Then we move to the next index, that is from index number 1. At index number 1 we have value is equal to 3, right? So again we try out all the j values from j is equal to 2 to n minus 1, and then take the valid what we call valid indexes where the range difference of the range satisfied, and then again update the dp values, right? Then we do the same thing from index 2 and index 3, like I have shown you only some part of it, right? So again we have updated our dp after processing index number 3. So this is our final dp, right? So if you see the value stored at n minus 1 is 3. That means the maximum jumps required to take from 0 to n minus 1 is 3, and that is our answer. So our answer is 3. So let's see the code part of it. So in the code part we have first taken the size, which is n, that is num size, and then we have declared a dp of the same size n, and initially declared all the values as -1. Then our base case is dp of 0 is equal to 0. Then we iterate from all the indexes from 0 to n, and then we see if our current state of, that is dp of I, is equal to -1, that means we haven't reached that state, so we skip that state. But if dp of I is not equal to -1, then we iterate over all the future states j from I plus 1 to n, and then we find the difference, that is nums of j minus nums of I. And if our difference is in the range minus target to target, then we mark dp of j is equal to maximum of the value stored and current value plus 1, right? Current jumps plus 1. So this way we'll reach all the states from I to j, and at the end what we'll do is we'll return dp of n minus 1, right? So this this approach of ours is worked because our n is equal to 1000 only. But what if n is greater than 1000? Then n square will not be feasible, it will give us tle. So then this approach would have been failed, and we have to think of some optimized solution, right? So what we will do is, why this approach is failing, because for here, for every j we have to scan all the previous indexes I. We have to scan all the previous indexes I, and which is making it slower, right? So so what so let's see the how we'll be optimizing it. So if you'll see the condition, our condition is that the difference should be from minus target to target, right? So if we bring nums of j here, it will become nums of j minus target, nums of I, and nums of j plus target, right? So if we rewrite the condition, this would have been like this way. Our nums of I would be in this range, right? From nums of j minus target to nums of j plus target, right? So for current index j we need all previous indexes, among all previous indexes whose values lies in that particular range. What we want that previous range, that previous index I, whose value lie in that particular range, and so that index lies in the particular range, and also it gives us the maximum value of the dp, right? So now if you see, our problem has been updated to a range problem, that is range maximum query, right? That is we have to find maximum value of dp of I in a range of indexes, right? For every current value, that is nums of j, what we need maximum value of dp of I. That means we need, for all indexes I lesser than j, we want that index who gives us a maximum value of the dp, right? And also that this range should be satisfied for that particular index, that is nums of j minus target should be lesser nums of j plus target, like that nums of I value should lie in the range, right? Then dp of j will be the best value that we get plus 1, right? So now we have the range queries. So as we know, for range queries we either use segment tree or Fenwick tree. So here we use segment tree because segment tree to gives us a query also, and it does the point update, that is update at one position. So both giving range maximum query and point updation, it does in log n time instead of of n time. So earlier our time complexity was big of n square, but now using segment tree it will be reduced to n log n, sorry, not n, it will be n log n, right? So we use segment tree, but there is one problem over here. See, in the constraints we are given that the values in the nums array can be from minus 10 ki power 9 to 10 ki power 9, minus 10 ki power 9 to 10 ki power 9, and it is not feasible for us, to build a segment tree whose size is 10 ki power 9. So what do we do? So we have to think. So we'll be using coordinate compression. Now what is coordinate compression? So let's see. Suppose we are given a nums array who has the values 1 3 6 4 1 2. So for coordinate compression, what we'll do is first we take unique sorted values of the nums array, right? So see, here the unique sorted values are 1 2 3 4 and 6, right? Then what we'll do is then we'll assign new indexes to these uh, compressed values. So 1 will be given index 0, 2 will be given index 1, 3 will be given index 2, 4 will be given index 3, and 6 will be given index number 4, right? So these are the new compressed indexes assigned to the nums values now. And now see, earlier how much values we have 6 values, but after compressing we have only 5 values. So now the value become small indexes, right? So now what will be our segment tree storing? So at compressed positions of value x, right, at compressed position of value x, what will be storing? We are storing the maximum dp value that we can achieve using the particular value x, right? So we'll be storing maximum dp value that we can achieve. So we'll try to understand it with the help of an example. So we have taken the same array 1 3 6 4 1 2 and our target is 2. So first we need to compress the indexes. So we first sort it. So we get 1 2 3 1 2 3 4 and 6. So 1 will get index number 0, 2 will get index number 1, 3 will get index 2, 4 will get index 3, and 6 will get index 4 in the compressed indexes. So now at step number 1, at index number 0, we have nums of 0. We have nums of 0 is equal to 1, right? We have nums of 0 is equal to 1. So and dp of 0 is equal to 0, right? We'll be starting from here and dp of 0 will be 0. So now we have to update the segment tree and we store. So value 1 will store for value 1 we store dp is equal to 0 in the segment tree, right? Then we go to next step. Now at next step we have nums of 1 which is 3. We have nums of 1 which is 3. So for 3 we will be finding what will the range of the previous values. What is the range of previous values? So 3 minus k and 3 plus k. So the range of previous is 1 to 5. So all the values in the range 1 to 5 are allowed for the current value. So now for these values we find the maximum dp value, right? So this is a range in what we call in the normal array, but see in compressed indexes, the value corresponding to these are 1 2 3 and 4, because if you see See, 6 is having index number 4. So our range was 1 to 5. Our range was 1 to 5. So what are the indexes? Index is 0, 1, 2 and 3 in that particular range, right? So for this particular range we have to find the compressed indexes. So the compressed indexes are 1, 2, 3 and 4. Now what we do is we'll query and we find the maximum dp among these values, right? But in currently in the segment tree we have value 1, that is dp of 0. So best value that we get is 0. And now we mark dp of 1 is equal to best plus 1. So best is 0 plus 1 is 1. So dp of 1 will be 1. So we update our tree, and value 3 will store dp as 1, right, in the segment tree. Then we move to step 3, and at step 3 we have taken nums of 3 is equal to 4. Nums of 3 is equal to 4. So again we found the allowed range, that is 4 minus 2 and 4 plus 2, that is 2 to 6. So this is our allowed range. Then we find the compressed indexes range, right? So compressed indexes range is for 2 to 6. For 2 to 6 our compressed indexes range is from 1 to 4. From 1 to 4 compressed indexes range is from 1 to 4. So now we'll query the maximum dp value in this range. And now suppose we get the best answer is 1, then we mark dp is 1 plus 1, we mark dp as 2 and then update our tree. So this way we'll do the query part and we'll do the updation part. If you don't know, if you don't know about segmentary, I have already explained you, I have already made a video on segmentary. You can watch out that video and you'll get it. So this way, using segmentary we could implement the solution and reduce our time from n square to n log n, right? So let's move to the code part. So in code we have implemented our segmentary class. In that we have taken integer variable n, which is the size of the array, and then our vector, or we can say array, to store the segment tree, right? So this is a constructor which will take the size and then declare tree of size 4n. I have already explained in that video. So make sure to watch out the video on segment tree before seeing this part, right? Because I explained why we take size as 4n in that video, right? Then this is our code for updation. So in update part we take the starting and ending range. So this is a range of the node, and we have to update index idx with value well. So if we reach, so this is our base case, that if we reach leaf node, that is starting range is equal to ending range, then we update tree of node is equal to maximum of tree of node comma value, right? So this way we update this node, and then after updating the node, then if this is not the case, then we take the mid part, then we find the middle value, and then check if index is lesser than middle, then we update the left child, else we update the right child. After updating the child we update the parent. So parent value is equal to maximum of value of left child or maximum of value of right child. So parent is equal to maximum of left child comma right child value, right? So this is our update part. Then we see the query function. So in query function there can be three cases: either no overlap, or complete overlap, or partial overlap. So in case of no overlap we return -1. In case of partial complete overlap we return the direct value, we directly return the value. In case of partial overlap we go to left child and right child and find the maximum value out of these two, right? Out of left child and right child. So this is query function. Then this is our main function. So in main function we have taken vector integer vals, that is we are doing coordinate compression, and then we are finding unique sorted values of the nums array, right? And then we are taking the size of the compressed values, and then made a segment tree of that compressed size, right? And then we have taken a dp of the same size and marked dp of 0 is equal to 0. Now we are finding the compressed index. We are finding the compressed index of nums of 0 in the wells array. So we are using lower bound wells dot begin wells dot end nums of 0. So it will gives us an in iterator in wells array whose size is equal to nums of 0, right? And then we are subtracting minus wells dot begin to convert that iterator to index, right? So we get our position 0. So now we update this position 0 with the dp value, that is 0, right? then then we have used a loop on from 1 to n on the nums array. So we get the left value and right value. So left value and right value is the uh, that is nums of j minus target and nums of j plus target. This is the left value and right value for the range in the nums array. Then for this range we have to find the compressed range also, compressed range in the wells array, so we find iterator of left value using lower bound, and then we do wells dot begin to make that iterator to index. So this will give us the left range. Similarly, to find the right range we will be using upper bound, and then we subtract this from the iterator value that we get. So now we have got the compressed range, so now in this compressed range we will find our maximum dp using the query function. We in the compressed range we find our what we call best value, and then if our best value is not equal to -1, then we update our dp value as best plus 1, right? And then we get our best value, then we have to update our current value, right? So again we have to find the uh, compressed index for nums of j in the wells dot array, and then we update this dp value at that particular index, right? And at the end we return dp of n minus 1. So this way we use segment tree and compressed indexes to solve this question properly. So I hope I am able to explain you the solution properly. So if you like the video, please make sure to like, share and subscribe the channel. Thank you.